Okay, so in our class, we have discussed about a perfect risk sharing. Um, so I'm leaving this one example that is quite famous that tested how the perfect risk sharing in the sense of uh, how the individual's consumption changes when there are changes happens in the aggregate consumption has been discussed. So let me come to this paper. So when we are trying to test this hypothesis that aggregate consumption affects the the individual's consumption as well, we need to assume some utility function. In this particular paper, she assumed two different kinds of utility functions, and in each of them, uh, she did with she tested the data for U.S. consumption expenditure with different kinds of consumption, total expenditure on consumption, expenditure on durables, on non-durables, on clothing and food, and different items, components of the total consumption. So in first of let's consider the exponential utility function. So C has taken this kind of exponential utility function. Then what we have to do is basically we have to relate somehow the individual's consumption or the changes in individual consumption with the aggregate consumption. Okay. So this is the utility function for individual J and it's written in the exponential form. Okay. At the moment, we don't need to worry about uh, all these coefficients unless you are thinking of taking this paper as your term paper. Okay. And we don't have to worry about the different states. Those are possible because, as you will see on the next slide, basically. So what's happened? It looks very complicated when you have three summations. So what we are going to do is we are going to talk one by one, then probably it will be easier to understand. So this is what we have inside the bracket is nothing but the exponential utility function, except we have new term that has come the probability of any state uh, coming to realization. So let's look at the first summation that we have the inside one is saying tau is equal to 1 to s, capital S. That means what we are doing is we are doing this summation over all the possible states and for individual j. So each individual can observe any of the possible state, right? And so that's why we are summing over it. And then we have this probability of that particular state happening, as we have done in our class as well. Now, each individual is going to discount it the with a time discount factor beta. That's what we have. Then look at the second summation. What the second summation is doing from t is equal to 0 to infinity. So this is infinite lived agent. So we are summing for each individual over all the time period those are possible. Okay. Then for each individual, we are giving some weight delta j that will go from j is equal to 1 to j. So what we have done for each individual, if there are capital J individuals, for each individual, we are going from 1 to j, and for each individual, we are going from time period 0 to infinity, and obviously in each time period, there are capital S possible states. So we are summing over all the possible states for all the possible time and for all the possible individuals. So that's why we have these three summations, and this is the budget constant that we have. Okay, so consumption is equal to the income in each state. This is also important to see that consumption from or income from one possible state cannot be transferred to another state, right? For example, if you have bad state, if you say, okay, we are talking of monsoon, there are three possibilities. One is good monsoon, then you will have a bumper crop, very good crop. Then you have average monsoon, and you will have average agriculture output and bad monsoon. Basically, this is almost like a drought, and you will have no crop basically in this year or very little crop in this year. So these are the possible state, right? But what is going to happen if you have a good monsoon, or let's say if you have the bad monsoon in any year, then you cannot transfer income from the good monsoon to the bad monsoon because only one state is going to be realized in any case, right? So uh, transfer of income, transfer of consumption from one state to another state is just not possible. Okay, so that's why we are talking of each possible state, whatever is the consumption for individual J and what is their income, and we are summing over all the consumption and all the income in each state S. Okay. Now, after doing the first differentiating and getting, we get the first order conditions like this. Um, Here we see this pi is constant, lambda j is also constant for individual j. So what we can do, sorry, not lambda j, so beta is constant because we have assumed that all the individuals have the same time preferences. So we can take this pi and beta on this side, and you will have a new variable that we are going to define by mu hat, that is mu over pi b raised to power t. And once taking them on the other side, also take log of on the both side, and you will have a relatively simple equation that says log of mu hat is equal to log of delta, sorry, yeah, lambda j minus sigma and all these things. Okay. Now, because we have j individuals, we can, and the only variable that we see here is the j, right? So this equation is for basically true for every j. So what you can do, now you can sum it over all the individuals j and divide by capital J. So you get this equation. And what we are going to do is we are going to define new variables where 1 over j and all this will have a new variable. Similarly, this will have, we will put as a new variable, and this we will define as a new variable. Okay. Important on the left side is what is this variable is 1 over j summation over the consumption of all the individuals j, right? This is the aggregate consumption. Okay. So now, eventually, we'll have the aggregate consumption, an equation that has the aggregate consumption. That's what we have defined here. And we have written this aggregate consumption. Okay. So now we have two equations. The earlier equation was for individual, equation 5 here. And this new equation we are calling equation 6 has aggregate consumption. What you can do is just subtract equation 5 or 6 from 5 and do little bit of algebra, and then you find, okay, consumption for um, individual J is equal to aggregate consumption, deviation of wealth, and some constant term over there for individual J. Now we are going to do one more thing because there are few things those are not our interest. For example, this deviation of wealth as well. So what we are going to do is write this equation in the lag form as well. So write it for agent J for time period t minus 1. This will be consumption t plus this remains the same because there is no time period time in it, and here you will have b j t minus 1 minus b a t. Okay, now subtract this from this and you will get delta, or the change in consumption for individual j is equal to the change in consumption for individual the aggregate consumption, and plus something that has everything basically this something. So now we are saying the change in consumption for individual J depends on the change in aggregate consumption plus few other things, or the changes happening in the life or the circumstances of individual J. This changes could have been the the change in the employment status, you lose the job, your salary goes down, your income changes, or any other condition that may be changing for individual J. So now basically we are approaching that can be used in a regression. But before going to that, we are going to discuss another utility function that she discussed in her paper, that is the power utility function. In this, she has taken utility is given by in this form. It looks quite complicated, but that's perfectly fine for us. We will see, we'll get a very similar equation to this one in the growth form, but have something similar meaning. So what we are going to do? So we are going to do the similar things. You have the utility function for individual j. Then, as we did earlier, here write the Lagrangian for with the new utility function. Just change the utility function over here. Do the first order differentiation. You will get a condition, obviously different one. Then take the log, do the summation, and after doing all these things, you will get this kind of equation, and where we will have to assume all these summation terms are some equal to, for example, where you have the consumption or the summation of the log of consumption for individual j, call it as the aggregate consumption, okay? And similarly, this coefficient over there. Now do the subtraction, and after doing all these things, you will get the change in log of consumption for individual j is equal to the change in log of aggregate consumption and the rest of the changes happening in the life of this individual j. Okay. So again, we are seeing that the change in log of consumption is positively related to the change in log of aggregate consumption. Okay. Okay. So once you have all these things, what you have to do is you have to take it to the data. So what she did, she took to the data of consumption expenditure survey that is being done in India. She did for USA, but if you want to do it for India, then you have the consumption expenditure survey uh, in India as well. So you can do or replicate this. In fact, there are some people who have already done it, but obviously you can do with the new data, with the new geography, and maybe new empirical methods. Okay. So when you take this to the data, what you can do is you can say, okay, I'm writing this regression equation where we are saying we have these coefficients in front of beta 1. We have beta 1 in front of the change in the aggregate consumption. We have beta 2 and in front of the change in the income. If you are taking income, you can take the change in the employment status as well, or you can have more than one changes happening in the household. Okay? Then you have the error term for these individuals, and obviously you include the coefficient term, the constant term as well. Okay. Now our hypothesis has to be, according to our theory, that beta 1 has to be equal to 1. That means the change in the consumption for individual j are one-to-one related with the changes in the aggregate consumption, and beta 2 has to be equal to 0. So these are our hypotheses. Similarly, for the log 1 as well, you can write in this format, and if you have the data, then it's quite easy task to do the regression, right? So now you will have two regression methods or model that you can test with the data. So let's come. So in the paper, you will find the results are given for 12 different categories. I've just picked some of them randomly. What we see in the first specification, where we are doing the change in the consumption is proportional to the change in the aggregate consumption. We see that, okay, beta 1 is close to 1 in most of the cases, right? You see, uh, either 1.01 or 0.99. So the coefficient is very close to 1. And if you look at the t value, you find okay, t values are quite large, obviously more than 2. So you can say beta 1 is significant in all these different kinds of consumption, the total consumption and the component of the consumption as well. You can see that it turns out to be significant in, I think, more than 8 or 10 cases out of 12. Look at the beta 2. Beta 2 is very close to 0, right? In each of these cases, and then look at the error and see what is the t-value. Here it is 1.5. In this case, it will turn out to be 3.3. Otherwise, it's again quite low. The t-values are much less than 2. And if you do a joint hypothesis test, that's beta 1 is equal to 0 and beta 2 is equal to 0, and do the F test, you find that it rejects this, you find the F test, this value is significant. That obviously indicates that in case of non-durables, this is not the case. Okay. So beta 1 is not equal to beta 1 is equal to 1 and beta 2 is equal to 0 is at least one of them is not satisfying this condition. We know that it's because of the income in this particular case that it fails, right? Because as I said, it is 3.3 in this case. The t value is 3.3 in this case. Okay? And then in the growth one, we find that it fails in many cases basically, though beta 1 comes very close to 1 here, close to 1 here, close to 1 here, and is also significant in every case. But if you look at the beta 2, is also coming significant. That should not have come according to our hypothesis. So in the empirical growth model, it fails on the joint hypothesis in many cases, or in the case I have taken here in all the cases, right? I took it just to make them symmetric, total consumption, non-durable service and food, similar things, but you can check in the paper for all the 12 cases. In some of the cases, even the joint hypothesis says that it satisfies. So depending on the model and also the specification, whether it's the growth in the growth form or just the change of the consumption, we might find different results, but largely it satisfies that beta 1 is equal to 1 and significant. That means the change in the aggregate consumption affects the individual's change in the consumption of individuals as well. So it seems that the perfect risk sharing is satisfied um, to some extent in this scenario. Obviously, it fails in some of the cases as well, but largely there seems to be with perfect risk sharing exist in the economy. Obviously, it will not be perfect because the markets are obviously not perfect. There are friction in the market and many other uh, and markets are not efficient and all these things happens. So well, this is a way of testing what we learn in our lectures. And as I said, if any of you is interested in turning this into term paper, it may be a good idea. I'm not saying that you will get more marks just because you will choose this method, but obviously it's a good uh, way of practicing the theory into our practical or practice. Okay, thank you.